What if Europa's seafloor isn't alive with activity after all? We'll discuss this week on Planetary Radio. I'm Sarah Al-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. This week, I'm joined by Paul Byrne, an associate professor of Earth, Environmental, and Planetary Sciences at Washington University in St. Louis. We'll talk about new research that suggests that the seafloor of Jupiter's moon Europa might be far quieter than scientists once hoped. And we'll talk about what that might mean for habitability beneath that moon's icy shell. We'll discuss how planetary geology shapes the potential for life on ocean worlds, and why a geologically quiet Europa is still absolutely worth exploring. Then Bruce Betts, our chief scientist, joins me for What's Up. Europa's seafloor might be quiet, but Saturn's moon Enceladus is an entirely different story. We'll talk a bit about the evidence for why we think there might be active hydrothermal vents within that moon. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Before we get on to our main topic for today, I wanted to keep you all updated on the progress for the Artemis 2 mission that's going to be flying humans around the moon soon. NASA's moved off of that February launch window after a 49-hour wet dress rehearsal that ran from January 31st through February 2nd. There was a liquid hydrogen leak during the fueling, so NASA is now targeting March as the earliest possible launch. We'll have many more lunar updates as we approach this launch, so keep your fingers crossed and send all of your best wishes to all of the Artemis crew. But back to the topic of Europa. It's one of the most promising ocean worlds in our solar system. Beneath that fractured icy shell lies a vast global ocean, one that may contain more liquid water than all of Earth's oceans combined. That possibility has made Europa a key target in the search for habitable environments beyond our planet. And soon, we'll be taking a much closer look at that moon. NASA's Europa Clipper mission and the European Space Agency's Jupiter Icy Moons Explorer, or JUICE mission, are both on the way to the Jovian system right now. Of course, JUICE's primary mission isn't to look at Europa, but still, having two flagship-style missions in the Jovian system at the same time that are just going to be looking at moons, that's going to teach us so much about what's going on within the system. But as we prepare to explore Europa up close, new research is challenging some of our assumptions about what might be happening deep below that ice. A study published in Nature Communications in January 2026 called Little to No Active Faulting Likely at Europa's Seafloor Today suggests exactly that Europa's seafloor might lack that kind of tectonic and hydrothermal activity that many scientists have associated with life on Earth. Rather than a churning, geologically active ocean floor, Europa's depths might be far calmer than we expected, which raises questions about how we think about habitability on ocean worlds. That study was led by Dr. Paul Byrne, an associate professor of Earth, Environmental, and Planetary Sciences at Washington University in St. Louis, where his research focuses on comparative planetary geology. He studies how the surfaces and interiors of worlds across our solar system form, evolve, and sometimes dramatically diverge. Paul's work spans planets and moons from Mercury to Europa, combining spacecraft data, numerical modeling, and Earth-based analog studies to understand the fundamental processes that shape planetary bodies. Earlier in his career, he was a messenger postdoctoral fellow at the Carnegie Institution for Science, where he worked on NASA's messenger mission to Mercury. He's since contributed research tied to major targets like Venus and Jupiter's icy moons. But beyond his academic work, Paul is also known for his thoughtful public science communication, previously on Twitter, but now on Blue Sky as the Planetary Guy. I spoke with Paul about what a quiet European seafloor might actually mean. Hey, Paul, thanks for joining.
Hey, Sarah, nice to be here.
You know, I had one of those funny moments when I saw your name at the front of this paper. I kept thinking, why does that name sound familiar? And then I realized you're the Planetary Guy. I've been following you online for years.
Yes, I'm the Planetary Guy. It's a mix of planetary science communication and complaining about Mars.
But now you're back with this new paper on Europa's seafloor. And Europa has long been considered one of the most promising places in the solar system in the search for life. And when people think about that, because it's an ocean world, they commonly see these hydrothermal vents in their heads, something like what we would have here on Earth. But your team's paper seems to indicate that Europa's seafloor actually might be very quiet. Why might a quiet seafloor on Europa indicate a lifeless ocean?
Okay, so to be clear, we don't know that it does. And this gets to a really complicated question, right? Which is like, not just what are the conditions you need for there to be life in an environment, or for what we would define as habitability, but are those conditions enough for there to be life there, or do you need something else? And the shorter answer is we don't really know, because we don't know a lot about abiogenesis, the formation of life from non-life. It happened at least once on Earth. It must have, because we're having this conversation. But we don't know the effects or the controls in that process. So we don't know if Europa is habitable based on what we think it has inside, or if it's inhabited. So we can't say definitively one way or another if our study in this case means it's more or less likely that there's life there. But what we can definitely say is, on the basis of the work we've done so far, it's probably not going to have those hydrothermal vents like we're picturing in our head.
Which could be a shame, but as you point out, might be a more complex question about how life develops in the universe. So, still worth pursuing, even if the seafloor is perhaps dead. How did you get into this? Like, why was this the question that you guys decided to pursue?
Right. So the question originally was with a co-author and a friend of mine, Christian. We were chatting one night, and I don't remember how the conversation got onto this topic, but both of us are interested in tectonics and what that does for planetary surfaces, and what you can tell from a planet's surface about its interior and its history by looking at its tectonic structures. Now, in the case of, say, Earth or the Moon, Mars, Mercury, Venus, that's a relatively easier thing to do because you can see those things, right? So why would we be thinking about the ocean worlds way out in the outer solar system? Well, basically, we were chatting, and one of us asked the other, what would the ocean floor of Europa, for example, look like? Would it be replete with towering volcanoes in lines like we see in part of Earth's ocean floors? Or would there be huge scarps and cliffs and rift valleys? And would there be the kinds of things you see on parts of Earth's ocean floor? Or would it be like what you see in the deep abyssal plains on Earth? Completely flat, really quiet, maybe some sediment. And I guess I sort of assumed that we would have known that already, just through kind of trying to figure out from first principles what it would be like. We are very far from being able to photograph the surface of Europa's seafloor. That would require technologies we don't have yet. And although I think it'd be worth doing, that I'm probably not going to live to see that. So we are kind of working from sort of a relatively limited data set. But basically, we were like, what would it look like if you were to fly over the ocean floor in a submarine, let's say, and take photos? And so we looked through the literature and found that there really wasn't a lot. There'd been a few papers, but very few that had really thought about what the actual geology of the ocean floor would look like. And that's probably not surprising because you cannot see it, but you can see the outer shell, which is this frozen ice shell. And it's got lots of fractures and lots of interesting stuff. And so it makes sense that much of the work looking at Europa over the past 40 years or so has really been focusing on the exterior, the bit that you can see. But to your point, Europa is really exciting as a potential astrobiological destination because we think it has the three major things that you need for an environment at least to be deemed habitable, right? Doesn't necessarily mean that it's inhabited, but it means that it might be able to support life, right? You need liquid water, which we suspect it does. Now, we do not know for absolute certainty there's liquid water ocean there. We strongly suspect it. NASA's Europa Clipper mission, one of its science goals is to definitively answer this question. And I think it will, and it'll tell us a lot about the ocean and the interior structure and layering and arrangement of things in Europa generally. Okay, so with liquid water you need, because anywhere on Earth we find liquid water, we find life. So, and we are, to use Star Trek's parlance, ugly bags of mostly water. Okay, so water is a big part of the life as we know it. Okay, there's a big caveat here, as we know it. It's very hard for us to think about life as we don't know it, because how would we even begin to test something, how to look for it? So we're thinking about life as we would be able to understand it. It might not work quite the same way, but it would be carbon-based and it would be water-based the way we are. Second thing you need is organic chemistry, because we are full of organic compounds. And there's good reason to think that Europa probably has a lot of this stuff, both on the basis of what we see on its exterior, but also that almost everywhere we've looked in the solar system, we find often complex organic molecules. We find them on Mercury and in comets. So this stuff is everywhere, which is really interesting because it means that, again, it's not life, but the building blocks of life are probably ubiquitous, which is exciting. And then the third thing we think you need for an environment to be deemed habitable is you need some kind of energy source. And on Earth, that energy comes from principally the sun if you're on the upper part. But we know since the 70s, when we discovered these so-called black smokers and white smokers, these hydrothermal vents deep in these seas, seafloor, that there are places on Earth where you can have a thriving biological ecosystem without any sunlight whatsoever. These things are completely detached from photosynthetic life. And they work on chemosynthesis. They're basically able to live off chemicals coming out of the water in these vents. And that's super exciting because the European seafloor is pitch black. There's miles of ocean and ice above it. So there's no sunlight getting down there. But if it happened to have the kinds of systems that we see, for example, on Earth's seafloors, well, then maybe that would provide a source of energy as well. And then the question is, where would that energy come from? One option is that you have heat in the inside anyway, because the planet started, or I think of these things as planets. Europa probably started off pretty hot, like most places did. It's got radioactive elements that decay, produce heat. Plus, Europa also is subject to tidal heating. It's like a much less dramatically crazy version of what you see for Io, which is by hands down the most volcanically active body in the solar system because it's squeezed between Jupiter and Europa and Ganymede. Europa isn't nearly as squeezed, but it's squeezed enough, we think, that there is a liquid water ocean there that would otherwise have frozen solid. So on the face of it, Europa's got the three things you need. It's got liquid water, it's got organic chemistry, and it's got an energy source. So maybe there's life there. And that got us thinking about, well, what could we say about what might be happening on the ocean floor? And to skip ahead to the end, the TLDR is that there's not a lot happening based on the assumptions we've made, which we can get into. But a big thing I really want to emphasize here is this is based on our understanding of Europa today. And something that is very difficult to kind of be precise about, but something we are confident in, is that these moons, when there are tidal effects at play, potentially go through periods of enhanced heating and enhanced geology, maybe for a few 100 million years, every 2 billion years or something, right? The actual frequency of that is not all that clear. But the idea is that Europa may have had a much more interesting middle age compared to where it is now for a time, which changes things. It could change the rate at which you have activity. There could be volcanism. There could be things happening on the ocean floor that would make it a lot more active chemically and potentially able to support chemical life than what it does today. So in our paper, we're kind of taking a first stab at what modern Europa's seafloor might be like. It doesn't necessarily rule out anything that happened in the past or perhaps even in the future. And again, we're not saying there's no life there because we don't know. And life is extremely resilient, and we know that on Earth. But again, I think we can rule out the idea that there's crazy big hydrothermal vents pumping these black smoker things into the ocean. That's probably not the case today.
Wouldn't that be fascinating, though, if we could get down in there and realize that in the past it was far more active? Like, what if there was life on Europa in the past that now is either no longer there or has evolved into some kind of, chemosynthetic creatures that now live on what remnants of chemistry is down there?
So this is the thing, right? And I mean, if you got down there in the submarine, you could imagine one idea might be that it was never all that interesting and that it's pretty inert and flat. Or maybe you see that today it's quiet as the grave, but there's remnant topography from a time when there was much more enhanced heating, and there's ancient, now long dead volcanoes slowly being eroded by these slow ocean currents in this extremely quiet, dead, calm ocean, but attesting to a period when there was a lot more activity. And, that wouldn't be the first place we'd see that. We look at, for example, the surface of the moon, Mercury, or Mars in particular, we see worlds that earlier in their life were much more active. Now, their geological history isn't quite the same trajectory as Europa's, but there are parallels. And you can imagine that maybe early on in solar system history, you had a lot of places that had a lot of stuff happening. And then over time, they basically run out of energy, even with tidal heating. And, when I step back from this, and we've been working on this project for about 9 years, and the pandemic and a bunch of other things got in the way and stuff. And eventually we kind of rebooted it. And we're now using it to sort of this first paper to build on subsequent ones to kind of expand this study. But, when we first started doing this and we found those first set of calculations, which never really changed, we refined everything a lot more, but they never really changed, which was that it doesn't look like there's a lot happening today. It kind of got me thinking about the fact that we look at these other places and we look at where these worlds had activity for a while, like Mars. There was massive building of huge volcanic constructs, an enormous amount of water pouring out of the crust billions of years ago. Or even Mercury, which built most of its crust in an extremely short amount of time. Even Mars had active volcanoes billions of years ago, but they don't today. And it kind of got me thinking about the idea that maybe we shouldn't be surprised that the only world in the inner solar system that is actively geologically working today is the largest one. It's the one we're on. And when we think about these other bodies, particularly say Europa, although Europa is a little bit smaller than the moon, when you take out the outer shell and the liquid water layer, Europa is a rocky body. It's a rocky world. It's got probably has an iron core, although the details of that are not clear, and Europa Clipper will help elaborate on that. But it does mean that we're talking about a rocky body smaller than the moon. And if we look at the moon, much of its geological history ended a very long time ago. So again, even with these periods of enhanced tidal heating, maybe it's not that surprising that the ocean floor of somewhere as small as Europa is pretty quiescent today.
I mean, this is clearly a very complex subject if you get into the actual paper, but generally, how do you try to determine the level of geologic activity on the seafloor of a distant moon under an ice sheet and under an ocean, which we can't penetrate?
That no one's ever seen.
Yeah,
right?
how do you try to figure that out?
Okay, so first off, it's best guess. And if we're wrong, great. That'd be great. But proving us right or wrong would be really difficult and requires probably getting into the ocean itself, right? So we are a ways off being able to go and test this. It is testable, but by our great descendants. So how do we start with this? So we make some basic assumptions. I mean, that's like anything like this. We have to make some basic assumptions. So for example, we assume that there is a seafloor. And that doesn't seem unreasonable, and people have been assuming this since the beginning. And the reason we assume that is because we have measurements of Europa in terms of its size, its diameter. We have an estimate for its mass, and we've got some very, very clever measurements that people have been able to determine using spacecraft radio transmissions and Doppler tracking of those radio transmissions that gives us an insight into how the internal structure of Europa is arranged and where all the heavy stuff is and where all the relatively less heavy stuff is. And what that tells us is Europa cannot be water all the way through. It's way too massive for that. So there's almost certainly rock and metal in there. Now, the exact proportions are there are error bars, right? We don't know for sure. But we can be reasonably certain that you have an outer ice layer, underneath you have a liquid water layer, and then you've got rock. We roughly know how far down that rock is. We don't know for sure, but our models aren't all that sensitive to whether it's off by a few, say, tens of kilometers. Okay, so it's rock. Well, we can look at all the rock in the inner solar system, and okay, I'm not a geochemist. I'm married to one. I'm not one. So I'm going to say something that's going to be anathema to geochemists, but not to normal people. Most of the rock is basalt, or in the US pronounces basalt, but it's basalt. And this stuff there's all kinds of different flavors of it, right? But functionally, it's the same rock. And so we might reasonably assume that that's what the seafloor is made of, or the precursor rock from which basalt is derived, which is a rock called peridotite, which is basically what Earth's mantle is made of. And it doesn't really matter which of the two it is, because from a mechanical perspective, in terms of thinking about faults and fractures, and I'll come back to why they're important in a minute, those two kinds of rock largely behave the same. So we're going to assume that it's a rock that's very common and then has properties that we understand pretty well. Why do fractures matter? When we look at these chemoautotrophic environments, these chemosynthetic places on Earth, far from sun, way deep down on the ocean floor, the way in which life is sustained, the bottom of the food chain are these little bugs, and these bugs live off things like hydrogen, and that hydrogen is produced through the reactions of water and rock. And it produces these chemical reactions that give rise to things like methane or hydrogen. And the way this happens is you have rock that is chemically unaltered. It's able to have this reaction with water. It touches the seawater, and you go through this process. And the most well-known one is called serpentinization, which is the process by which you make a rock called serpentinite, which is cool and kind of waxy and weird looking. It looks something like Slytherin would have, right? So this kind of weird darky green thing. The point anyway is that when you have rock reacting with water to produce serpentinite, you produce gases that these bugs could eat. The way you get rock reacting with water is to expose new rock to that water. Now, one way of doing that is you can have volcanism. You can have lava pouring onto the ground. The ground being the seafloor. And the lava's come from depth, and it's got all these chemicals in it, and it can react mineralogically with the water to produce this hydrogen, let's say. Another way is if you have fractures that are in the rock, water could get down those fractures. Anytime you've ever seen like the side of a tunnel with concrete with cracks in it, water gets down there. It's extremely good at doing that. As far down as we've drilled on Earth, anywhere it's wet. Like the hydrosphere gets all the way down, kilometers down. So as long as you some way of fracturing the rock, you can get water down there. I've seen a lot of rocks. I've never seen a rock that isn't fractured. There's always fractures somehow in rock, right? You don't want many if you're going to build a bridge or a tunnel, but there's always going to be a few, right? So we assume in our model that there are fractures there. It doesn't matter how they're there. We just assume that there are. If there are no fractures, things get really hard. We'll come back to that in a sec. So we think we need fracturing because that fracturing allows water to get down. Once the water gets down and touches the rock and reacts, there will come a point when that water and the rock are now chemically equilibrated. There's no more potential for this reaction. And so the process of producing things like hydrogen goes away. And we know this happens on Earth. We've studied this for more than 100 years. But on Earth, especially, though not exclusively, at these big black and white smokers, these big hydrothermal vent systems, they're on or nearby these huge spreading centers where two tectonic plates are pulling themselves apart because this planet has a lot of heat left inside and there's a lot of stuff happening. So we've a lot of mechanisms that can generate new fractures. So even when the old fractures actually, not just that they stop reacting, but they actually fill up with stuff, with chemicals that precipitate. And it's a very effective way of locking in and making that fracture no longer work. So the planet makes new ones. It also is producing gobs, geological term, of lava pouring out of the ground. So when we have active geology, we can imagine a scenario where we can continually expose fresh, unreacted rock to that water to continue these reactions and help feed these little bugs. But if for some reason these reactions stop, then the food source goes away, right? Because there isn't the sunlight, which is there all the time. So we wanted to know, we didn't explicitly look at volcanism. We had a companion paper that came out last year. I was co-author on that, led by a guy called Austin Green. And Austin worked with his co-eyes to show that volcanism, seafloor volcanic activity, is very unlikely today in the modern era. That doesn't mean there isn't necessarily melt or magma at great depth, but it has a hell of a time getting to the surface. So that's probably not a reliable way you could, at least on any kind of regular basis, produce new rock and introduce it to the water, right? So that's not an option for producing these chemical reactions. Okay, well, what about fracturing? So what we did was we assume that the rock is of a type that we understand pretty well. And then we use some pretty well-established, this is like reservoir mechanics. It's how we figure out the strength of where we're drilling for oil and gas or mines. We have a good understanding based on a couple hundred years of understanding how rocks behave under different stress regimes as to how strong or not that rock is going to be and how likely it is to have fractures. And if you have a fracture, how likely you are to be able to move that fracture and get water down there, exposing that water to new rock and keeping these chemical reactions going. So that's what we did. We used these approaches and we said, if you make the following assumptions, how strong is the rock? Right, that's the first step. There's two steps to this. Now, to be clear, we didn't want to presuppose the answer, but we did want to see what is the easiest way you can make this happen. So, for example, I said earlier that every rock that I've ever seen has fractures in it. So we assume there are fractures in the ocean floor. If we didn't assume that, suddenly the ocean floor becomes remarkably stronger. But I don't think that's realistic because any rock we see anywhere has got fractures in it. We also assume that the rock itself is pretty weak. That's going to make it easier to make a fracture or to move a fracture relative to another if it's there already. So we've made a bunch of assumptions that actually weaken the rock and make it as reasonably weak as we can think we can justify. Right? We're not saying that it's made of cardboard. That's not scientifically defensible. But we are saying that this stuff is heavily fractured. It's very weak. And with all those conditions set, how strong is it? So we do the calculations and we get some numbers. The second part then is, okay, so we now know how strong it is. That doesn't mean much if we don't know what likely mechanisms might be able to overcome that strength and either make new fractures or reactivate old ones. So then we think about what mechanisms there are to drive stress. Now, I said on Earth, where you have these big systems, you generally see these things associated with huge tectonic processes where plate boundaries are pulling themselves apart. And there's an enormous amount of energy there. It is true, and I'll come back to this in a few minutes, there are places on Earth where you have water percolating through rock far away from these big hot systems, right? So these off-ridge hydrothermal systems. So we'll put a pin in that. We'll come back in a few minutes. But we're mainly thinking, we now know how strong the ocean floor is, we think, for a set of defensible assumptions. What are the mechanisms that can act on it? So one is tidal stresses. We know that tidal heating is wreaking havoc on Io, and it's certainly deformed the icy shell of Europa. So What is that mechanism doing to the ocean floor? Turns out that it's really not doing a lot. In fact, that the stress the ocean floor is feeling is much, much below the stress of required to break it. So we were like, well, what happens if these tidal stresses are working on the rock for billions of years? Surely that might weaken a rock enough that it actually is way less strong than we think it is. So we thought about that too. We went through the literature. Turns out nobody could agree on how much rock gets weakened, but there are estimates. So we picked an estimate. We actually don't know that the tides are weakening the rock at all. It is possible that you could apply a stress to the rock a little bit for functionally ever, and it will never damage the rock. But we're going to assume that it does. So we were like, what if the rock is a quarter of the strength that it has, that we think it has? Even if it's a quarter of the strength, it actually doesn't really make much difference. There's not a lot happening. Okay, so tides, today at least, not an obvious source. Now, tides don't do a lot of stuff on Earth in the ocean floor, so maybe that's not that surprising. We thought also, I was thinking about our assumptions, we also assumed that it's wet all the way down, which actually makes the rock a lot weaker. If you add water to rock, it really weakens it. That's not something that's all that realistic, but we're sticking with it. If it was drier than we think it is, it becomes stronger and therefore even less likely to fail, right? So we're always trying to err on the side of we're overestimating how strong the rock is. And in fact, it's probably weaker still. So we're thinking about what other mechanisms are. There's a few other mechanisms that can act. So we know, for example, looking at Mercury and Mars and the Moon, that one of these things these worlds have experienced over time is they've physically gotten smaller as they cool down. And this process, we call it global contraction. And I did a lot of work on this for Mercury. It probably has had some effect on Earth, but how you would distinguish that from all the plate tectonic stuff we have is extremely difficult. But as worlds get older, they cool down. So when that happens, you can potentially have tectonic structures that would make fractures, maybe. Probably not great ones, but they might make a few. So we thought about that process. Turns out it's probably not really a particularly reliable way. The inside of Europa may have closed a little bit, and in doing so might have made fractures. But whether or not you're generating enough to ever get water percolating down to reach unreacted rock seems unlikely on the basis of how we understand faults to work on Earth. So we thought about, if you have, for example, water and rock touching and they produce this serpentinization process, interestingly, because of how you arrange the molecules in that mineral, it actually expands a little bit. And in doing so, that creates a stress of its own. So we thought about that process. But it turns out that although that's a very effective way of making rocks crack, that process dies out with depth because you have more and more pressure compressing everything and actually stops that process happening. So you might have the upper few kilometers cracked and ridden with fractures. But then you get to this other problem, which is that the water will get down and start to react with the rock. And that's happy and great. But over time, once those reactions stop and everything has come to chemical equilibrium, there's no more way of you getting more fractures. And so the process comes to an end. So we thought about these mechanisms in the context of how strong we think the rock is for all of these assumptions. And again, because we've so little information, we make assumptions that the rock is weak to begin with, and then we try and figure out, it's hydrated, it's got all this water all the way, it's already got fractures somehow. And for all that, there's very little happening. And even if there's stuff happening every million years, so for example, we use the moon in the paper as a comparison, because there's what we call geologically young fractures in the moon that probably are from the moon contracting. And some of these fractures are the kinds of things that would be helpful for water to get down. Now, they're very small. But the problem is when you think about the moon and we use the word young, the youngest fractures in the moon are estimated to be between 12 and 50 million years old. That's not young. 66 million years ago, the dinosaurs got whacked, right? So 50 million years is not young. But in the context of lunar history, it is. But even if you had a fall slipping every million years, I just made that number up. It seems unlikely that there's going to be a whole profusion of life going, oh, great, maybe some weirdo life can go super dormant for 1 million years. We're not ruling anything out, and we do not take a biological view of this. We beyond thinking about what an ecosystem might need in terms of chemistry. So maybe some sort of weirdo alien bug can live for a few days every 1 million years. Okay, but in terms of there being a mainstream ecosystem that would look something similar to what we see on Earth, it's unlikely. Now, there's a couple of big caveats here. We know on Earth, for example, that, like I said earlier, there are these big hydrothermal systems that can exist far from where the really big action is. They're slower, they're cooler, they're a little more reserved and calm than their crazy cousins who were at the spreading centers. So maybe you can imagine a scenario where very, very slow processes happening where water and rock are percolating down. But again, the issue is at some point you come to the scenario where the rock and the water have chemically equilibrated and the game is over. So unless you have some way of introducing new fresh rock for those new reactions, it's very difficult to imagine how you sustain an ecosystem. And that is the word that we're kind of coming to in terms of thinking about this study. It is worth pointing out too that on Earth, the energy generated by radioactive decay can also produce essentially chemicals that bugs can eat. And by bugs, I'm not a biologist. I'm talking about microbes, not like crawlies. But the idea is that there are surely radioactive elements inside Europa, as there are in the inner solar system worlds. And so it could be that those things are slowly decaying and there is an energy source, but it's not from the normal water-rock reactions. It's because of this radioactive decay. Now, that's something we haven't really considered. We think we acknowledge it in the paper, but that's sort of future work for us to do. But even so, the rates of energy availability, the rates of chemical energy from those reactions are probably going to be relatively low. So again, best case scenario in the modern era, we're talking about very low levels of energy that would sustain an ecosystem. And so it requires us getting creative to think about where in this sort of broad parameter space of life, where are the corners left where something might plausibly be able to hang on to today.
We'll be right back with the rest of my interview with Paul Byrne after the short break.
Hi, y'all. LeVar Burton here. Through my roles on Star Trek and Reading Rainbow, I have seen generations of curious minds inspired by the strange new worlds explored in books and on television. I know how important it is to encourage that curiosity in a young explorer's life. That's why I'm excited to share with you a new program from my friends at the Planetary Society. It's called the Planetary Academy, and anyone can join. Designed for ages 5 through 9 by Bill Nye and the curriculum experts at the Planetary Society, the Planetary Academy is a special membership subscription for kids and families who love space. Members get quarterly mailed packages that take them on learning adventures through the many worlds of our solar system and beyond. Each package includes images and factoids, hands-on activities, experiments and games, and special surprises. A lifelong passion for space, science, and discovery starts when we're young. Give the gift of the cosmos to the explorer in your life.
Yeah, it kind of shocked me when I was first studying planetary science, this idea that the internal temperature of any body, like so much of it actually is that radioactive decay, right? But if we're just looking at the internal heat of this body, at this point, how much of the residual heat from its formation can still be left? And is there even a potential for it to shrink much more?
So this is the thing. I don't know. I'm not sure it is known. One would have to do the same thing we did, right? Which is basically you make some assumptions. We have a rough idea of how big it is. You would make some assumptions about what the abundance of those radioactive elements are. About half of the heat coming from Earth today is from radioactive decay in the mantle. The other half, roughly, is from the actual heat of formation and accretion of the planet, which I think is wild, right? I mean, that happened 4.5 billion years ago. But, it's interesting to think about the fact that you might have heat coming up, and it might be more than 0 Celsius to keep that ocean from freezing, and then squeezing from the tidal stresses will also help keep that ocean from freezing. But just because you have heat doesn't mean you have activity. And so, I think about Mercury, for example. Mercury has a liquid iron core, probably has a solid iron core as well, because it has an internally generated magnetic field today. It has a relatively thin mantle. It has lots of stuff happen in the past, but even though the inside is still thousands of degrees and space is 0, there's virtually no evidence for ongoing geological activity on Mercury. There's some interesting chemical stuff happening that makes these kind of like erosional structures, the sublimation structures we call hollows, which were a total surprise. But we don't see lavas that are a few million years old, and we don't see tectonic structures that are huge and fresh, like big fault traces on Earth, or one might say Venus. So it's sort of consistent with the idea that you might still have heat in the inside. You might have enough heat to stop the ocean from freezing, but that doesn't translate to active geology on any time scale that would be beneficial to life. And so I think the lesson we're taking from this, so I am 100% certain that Mars will erupt again. The youngest known lava flow, to my knowledge, on Mars on the basis of crater statistics is 2 million years old. There's no way that thing erupted 2 million years ago and just stopped for a planet that's 4,500 million years old. But you can imagine that if you were to plot geological stuff versus time, so geological stuff goes on the y-axis, the vertical axis, and time is on the x-axis. You start off at the top corner with lots of stuff. And in most of these worlds, based on the geology we can see, that curve drops pretty fast. And then there's probably a super long tail, almost asymptotically to the x-axis. So you might still have some stuff happening. Is it enough to support an ecosystem? That is the question we have to ask. And so personally, what I've taken from this study is we are entirely agnostic about the possibility of Europa having had much more activity in the past. I think it almost certainly did. That potentially actually sets up the conditions for what might be there today. One of the downsides is if it did have a lot of activity earlier in its life, a lot of those reactions might already have happened and they're not available anymore. But it got me thinking about the fact that maybe it's not that difficult. This is just my own conjecture. This isn't something we could put in the paper, not yet. Maybe it's not that difficult to make an environment that can support life. Maybe it's really difficult to keep that environment over geological time. And again, I come back to the fact that the one place we know in the solar system that has had liquid water stable on its surface for its entire geological history, almost, is the largest rocky world in the solar system. It's Earth. And so it kind of makes me wonder that maybe if you go back 3-4 billion years ago, a lot of places might have been potentially certainly habitable and who knows, maybe even inhabited. But keeping things going that can sustain life there, I think is exceptionally tricky.
Well, even on Earth, over the course of, hundreds of millions of years even, which is relatively short, we've seen massive changes that have led to mass die-offs of life all across this planet, right? And even now, we're in the midst of a situation that is going to be impacting life going forward, right? So it's totally not inconceivable. And people ask me frequently, what do you think about life in the universe beyond Earth? Do you think it exists? I'm like, I'm sure it's there somewhere, right? But how long does it exist? And does it reach that point where it's intelligent? And even when it does, how long does it live beyond there? Is there some kind of great filter? And is that why we see that or at least we think we're alone in the universe, right? There's so much there. But I think it does come down to this basic idea, right? Like, even if something is habitable, that's a temporary situation in all cases.
Yes, it is. You know what? One of the things that I teach this class where we look at Earth history, past and future, and it's one of my favorite classes because it gets real kind of, Armageddon, Deep Impact, kind of like it gets real grim at the end. So we have these working hypotheses, right? That like Venus, for example, which is a world I cannot come on a show and not talk about. Venus, one possibility is that Venus was originally much more habitable and clement than it is today. We don't know that for sure, but it's one of the possibilities. But even thinking about our own world, the working assumption is probably, although it's very hard to test this, thankfully, as the sun continues to brighten and get more luminous through time, eventually surface temperatures will rise on Earth enough that it will trigger a runaway greenhouse. And once that happens, our oceans evaporate and then eventually get photodissociated in the atmosphere and we lose the water and the oxygen has to go somewhere. But the point is that we lose our oceans and the planet desiccates. And so there is a possibility that in 1 billion years or 1.5 billion years, the numbers are kind of fuzzy, Earth may end up coming to look like Venus, climatically and geologically. Plate tectonics stop because you need liquid water to lubricate those plates. So you can imagine that our own world is functionally going to look very different in, say, 2 billion years. And yet there's another 5 ahead of us before the sun enters the red giant phase. But even 4 billion years ago, the planet was probably orange. There are studies suggesting that on the basis of hydrocarbon hazes in the atmosphere of a much cooler surface, there might even have been much more carbon dioxide, preventing the planet from freezing over completely. I mean, Earth, and there was no land for the first billion years. So even our own world looked weirdly different, even though there was probably life of some kind on it. But our own world has managed to keep its climate stable enough that liquid water has remained stable on the surface, which is a pretty narrow range, over its history. It's not clear if that's something we can reasonably expect all large rocky worlds to do. That's one of the reasons why Venus excites me. It's because we have a world right next door that something bad happened to it, either early on or later in its life. And I think one of the reasons why this is such an important question for us generally, to exactly the point you said about how long can you sustain these habitable environments, as we start to find more and more Earth-sized worlds and super Earths orbiting other stars, Are we going to, and I think we'll have an answer to this question in the next 30 or 40 years, which I think is really exciting. Are many of these worlds that are consistent with having a nitrogen and oxygen, or even just a mainly nitrogen atmosphere and surface pressures and temperatures that are conducive to liquid water? That might potentially be a place where you could have plate tectonics, where you could have continents forming, where maybe you even had life. Or are we going to find most rocky worlds that are big with a 97% CO2 atmosphere, really high surface temperatures, because they're all in post-runaway greenhouse states? Because maybe that's the current or the common outcome for a large rocky world, and Earth's the freak. So these are kind of foundational questions. And the Europa paper kind of gets at the idea generally, what does it take to keep an ecosystem, an environment, if you can keep it?
It's fascinating, too, that even in the context where you assume mechanically weak seafloor, even in that scenario, we're still not getting the hydrothermal vents that we were hoping for, right? So, I mean...
we tried really hard to what can we do that we can get away with scientifically without, invoking that it's made of Lego or something, where we can try to make it as weak and readily able to react as possible. And like I said, one of the kind of weird catch-22s is that if we make it weaker, we actually have to already invoke that it has already reacted with the water to make it weak. So actually, what helps making fractures actually doesn't help us producing the reactions we would need to potentially support an ecosystem. So, it's a hard question. It's a difficult question to answer. But again, stepping back, just simply looking on the basis of size, zeroth order estimates of where stuff happens. The bigger you are, the more stuff you have happen to you. And whether Venus is active today and the extent to which it's active is a big open question I'm hoping we'll answer soon. But it's really the only other solar system world where we're thinking about that there's probably stuff happening today. And like I say, the only other place aside from Earth and Venus is Io, where we know, I can tell you with absolute certainty right now, there are volcanoes erupting on Io. And the reason is because it's in this very specific condition where it happens to be in this tug between Europa, Ganymede, and Jupiter. That's not a condition most of these other worlds experience. So yeah, stuff today is probably really hard to find.
Probably. Although I'm really glad every world isn't Io. That place is absolutely terrifying.
Yeah, I mean, the fact that it's got no impact craters, or maybe there was a poster a few years ago proposing that they might have found one impact crater. I mean, Io is kind of horrifying, but it's also really cool. And the fact that it's just got these huge fountains of stuff going hundreds of kilometers into space and falling down. And every time we've flown past it, it looks different, which means you've got to redraw the maps. I mean, that's kind of cool. Planet hell, really.
Really, though. I'm glad we're going to have so many different spacecraft in that system. We've got Juno looking at it now, but
right.
the Jupiter Icy Moons Explorer is on the way to that system, and we've got Europa Clipper on the way, which brings me to my next question, which is that there's so much we don't know about whether there is a liquid water ocean, how thick that ice crust is, how how thick the core of the planet is. That there are all these unknowns, but with the information we'll get from this spacecraft, even though we can't penetrate beneath the ice, can we still gain enough information to try to suss out whether or not that this is actually the case?
So we'll definitely get more information than we have now. So for example, we'll definitely get a sense of, I'm hoping, where that ocean ice interface is. It'll tell us where the interface between the ocean and the outer shell is. We'll also, I'm hoping, get information on where the ocean floor is, and that'll give us a more accurate constraint on what that pressure, basically what that overburden of all that water is doing to the rock. But we'll also be able to get a better sense of what the overall effect of the tides from Jupiter and the nearby moons are on Europa. It's possible, depending on the gravity field. There are papers in which people have proposed that you may be able to detect, even if it's remnant volcanism on the ocean floor, even if it's billions of years old, it may show up on a gravity signature, depending on how low you get and what the quality of the data are. So it's possible we would actually be able to detect something of the ocean floor itself. There's an unknown and an uncertainty there, but Clipper is going to look for it. The team knows that's the thing they want to look for. There's also the issue that we don't have a good sense of what the total shell looks like at high resolution. We'll get those data from Clipper. We'll also get much more information on what the deformation of that shell is, which will give us much more information on what that tidal history is and how much stress there is from the tide. And there's also the possibility, there was a paper in 2014 using Hubble data in which people reported potentially detecting a plume coming from Europa. Now, the work done since then has not been able to find evidence for those plumes. So either that initial detection was not real or it was an impact. let's say, that could have thrown up debris from the ice shell, or it was a plume and it just takes every 10 or 15 years to go off, right? We have no idea, even if they are there, what the kind of cadence of eruptions or pluming activity would be. So having Clipper there, and hopefully having Clipper there for a long time, is a function of how it's getting on in that high radiation environment. Although, again, by virtue of how its orbit's designed, it's going to spend the vast majority of its life far from those really high ionizing radiation belts. But Clipper is going to be invaluable for us to get a sense of understanding Europa properly, not just its surface or its shape, but also what's happening in the interior. So it's going to make a big difference in helping us refine our ideas for how these worlds evolve and what that means for example, an earlier period of enhanced tidal heating far beyond what it has today that could potentially have driven activity of the ocean floor. But it's not going to observe that. Nothing can observe the ocean floor unless and until you get into it. And the technology required for that is formidable, right? You've not only have to land on the surface and somehow not die within a few days because of the radiation, but then get something into the interior, get it through the shell. Clipper is going to be invaluable for telling us how thick that shell is, because there are two n-member models, one where it's relatively thin and one where it's relatively thick. And of course, those numbers are relative. They're still kilometers thick. Getting any kind of technology through that and having it work and then broadcast to the surface is, again, not a trivial engineering technical problem. But if we don't try, we'll never do it. So one could imagine a situation where maybe later this century, we do have a little, hopefully sterilized thing, so we're not killing anything that is there, swimming down. Now, of course, we'd have to make this thing operate 100 kilometers down, although the pressure would be comparable to the ocean floor on Earth. It's about 14 kilometers down on Earth equivalent, so it's a little bit deeper than the current deepest part of the ocean floor. But it's not insurmountable. We can make things that can accommodate those stresses. So maybe in the future, we'll have something going down there and it'll take photos. And maybe we're going to see nothing. There'll just be nothing. It'll be completely tectonically and volcanically quiescent. There'll be thick sediment of compounds that precipitate out of the ocean, covering everything, and it'll be boring. That'll still be an instructive thing to learn. Or maybe it's going to be replete with activity, or maybe it'll be dead, but there'll be lots of evidence for there having once had been stuff there. Any of those answers is important because they tell us what we can expect in terms of these ecosystems and these habitats generally. So even if it's going to be decades or perhaps even a century away, I'm hoping eventually someone's going to have something under that ice shell to go down, photograph the surface. And if I'm wrong, I'll be dead and it won't matter. But either way, it'll be instructive. And it really will be part of our understanding generally of characterizing potential habitats in the solar system and then potentially beyond.
I've seen some people have some really interesting ideas of ways that they can get beneath that ice shell. You know, I go to NASA's Innovative Advanced Concept Symposium every year, and oh my gosh, the nuclear robots that melt the ice down, or the systems of cabling that they've designed that would be able to deal with the fact that the ice freezes around the cables as this thing descends down into the ocean. Yeah. There are so many interesting questions there. I mean, like, even if you get it down in there, how to communicate back to the surface, right?
Yes, exactly. Yeah.
But I want to know. I want to know what's going on down there.
If we don't try, we're not going to build the technology to do it. And of course, one could also say, once you've done this for one world, he says, not an engineer, glibly, how hard can it be to build this thing for Ganymede or for Enceladus or for Triton or even Pluto? Right. If we have it's a little bit like developing rovers for Mars or aerial robots for Venus. Once you have a handle on what that technology looks like, one might start to think about how you would apply it to other places too. Because of course, this question isn't just about Europa. Right. Even if Europa is our best, most promising place we might think today, and it has captured people's imagination for decades, there are other potential or likely, or in the case of Enceladus, definitively known ocean worlds in the solar system. And so I think it becomes very important to think about not just one world in particular, but what this kind of environment is like generally. And although there's no such example in the solar system, there are places we think might be giant versions of this. Imagine an Earth-sized world with a huge amount of ocean on top, way more than the 4-kilometer average depth of ours. That could be 100 kilometers or even more. What does that mean for those worlds? Because a lot of the conditions that we think don't apply to Europa because of its size could well apply to a much larger ocean world, like the likes of which we don't have in the system today. And so maybe there is intelligent life. Maybe most of it is submarine, is marine life existing in Earth-sized or super Earth ocean worlds. And they don't care about making radios and broadcasting to us, but they have culture and history. Who knows? But again, anything we do to help us understand these environments and their rarity or not, and their activity or not, is another step toward understanding the kinds of conditions you need generally for life to emerge and for it to be sustained.
Well, all this makes me think not only do we need more information about Europa, but I want a follow-on mission to go to Enceladus. Because not only have we flown through those plumes and verified that there's probably hydrothermal activity down there, but all the necessary chemicals for life, as we said, which are just peppered all over the solar system. I want to be able to compare these two worlds. And I'm hoping because there's plume activity there, it might be a little easier to get something down into that ocean. We just have to find a crack big enough.
I mean, this is the thing. And this is not to besmirch Europa at all, but Europa is challenging because of the radiation from Jupiter. Enceladus does not have that same condition, and it's so much smaller that the gravity is lower, so the amount of chemical energy or thrust you need to land isn't as... Again, this is not to trivialize any of this, because getting something out there and making it work after the long cruise phase and then moving or roving or diving on the surface is not easy and is expensive. But one can imagine a scenario where maybe sooner than for Europa's seafloor, we have something looking at Enceladus's seafloor. And even that's going to be instructive. The size is very different. And I think if there is activity in Enceladus today, it's probably not from primordial or radiogenic activity. It's probably from those tides. But to your point exactly, we do have very strong evidence that the inside is a wet rock of some kind, and that wet rock is interacting with water. So let's get down there and see what those reaction rates are. Let's see what the compounds are. Let's see. And just because we don't find life, we don't know if there will be life there or not, doesn't mean that it's not an important thing to understand what makes an environment habitable in the first instance. And maybe we do. Maybe we go down there and there's stuff crawling all over the camera. Who knows, right? But that's why we explore, because we don't know. And even if, and this is the thing that I've also kind of taken from this study, because when I talk with people about it, often people kind of express a disappointment that we sort of like, we have not ruled out life on Europa. We've certainly said that it's probably more difficult to sustain today than we might have thought before. But, when I worked on Mercury, no one, I don't think ever credibly has said, oh, Mercury might have had life or has life today, because, oh my God, it doesn't, right? But that doesn't mean that it's not a fabulously interesting place. And so one of the things that kind of enthuses me about this is that, like, even if there's no life at all, okay, that's still important. That's still useful for us to understand. Let's figure out what would it take for there to be life there, or what would it take for the environment to be what we might consider habitable. But even the uninhabitable environments are still worthy of exploration. And so even if in 100 years we show definitively that Europa never had life, I'd hate to think that would somehow herald the end of us exploring it, because I don't think it's the only reason why we should explore. It's probably the most compelling reason. But all these weirdo worlds to me are cool, whether they've life on them or not. And I think we should explore all of them.
It just blows up my mind entirely that it was not that long ago that we didn't even know most of these worlds existed. And here we are now having a complex conversation about, comparative planetary geology and the depths of ocean moons all across our solar system, and what that might mean for the prevalence of life in the broader universe, right?
Yeah, like we are privileged to be doing this.
Absolutely. And we're one of the first generations to ever be able to even get to ask these questions, let alone try to suss it out. So I'm excited no matter what it is, as much as I would love to have little eyeless shrimp living in Europa, right? There's plenty of other places we could go. Well, good luck to you and all of your co-investigators on the research going forward. And I'm sure we'll get more information on this in the future, especially when Europa Clipper gets there. How excited are you for that?
I am super excited. I was there at the Clipper launch. I watched that thing pound into the sky on a Falcon Heavy, and I cannot wait to see the data. I mean, we've gotten some of the instruments have been checked out in their flyby of Mars. Clipper has returned images of 3i Atlas, which is kind of wild.
Right.
But when this thing gets there, the pictures we're going to get, I mean, every time we send a spacecraft to a place, even one we've been to before, and we set it with more modern instrumentation, we see more crazy stuff that we never thought we'd see. And then we're like, oh my God, my mind is blown. And I think at the very least, what that has told me is to just expect the unexpected. We're going to see stuff on the surface that we didn't think that would be there, and that are going to raise all these new questions in addition to all the ones that we already have. So I can't wait for Clipper to get there. And especially with JUICE, when those two spacecraft doing complementary observations, and if you look at how their orbits are thought to evolve over time, they will be able to do simultaneous observations of one body. I mean, we've never had two flagships of that type doing that kind of science. That's actually what I would love to see much more of in the 30s and 40s and beyond.
Thank you so much, Paul.
Thanks, Sarah.
We've been discussing Europa's seafloor. But a little further from the sun, Saturn's moon Enceladus is another story. We have quite a bit of evidence that that moon has active hydrothermal vents. Our chief scientist, Dr. Bruce Best, joins me to discuss now in What's Up. Hey, Bruce.
Hello.
Okay, so if I told you that Europa's seafloor was absolutely dead, would that make you sad, or is that just, normal Bruce thought?
Yeah, that would make me a little bit sad, but it's just part of gaining knowledge of our solar system, and it's not like we killed them.
Truth. Oh, man. I just hope, we're super, super careful about planetary protection and things like that when we decide to drop little submarines into these ocean worlds someday, because can you imagine? No, we're not going to imagine. It's going to be great if we ever explore life out there in the universe. We're not going to get them sick, and they're not going to get us sick. Fingers crossed.
Well, there's more than fingers crossed. There are pretty compelling arguments that, especially if they're evolving differently, or even if they're not, the fact that you would happen to hit a strain. I mean, if you look at even on Earth with all the coevolution of all sorts of stuff, there aren't too many things that hop species, even that are kind of in the same, territory of the biological tree, but to find something. But this is, by the way, from talking to actual real biologists, not just me spitballing. So I'm hopeful that yes, you should be careful, but it's not something that is very likely that you're going to run into something that just happens to have evolved to attack something that isn't human, but attacks humans. So
you're right. That makes me feel better, actually, genuinely. But, setting Europa aside, there are all kinds of ocean worlds that we can explore that might have life, right? And anytime someone asks me about where I think we're most likely to find life off of Earth earliest, I always say Enceladus, even though I think we're going to be going to Europa first, so we get more of the data there early. But Enceladus is my best bet, both because of the plumes, but also because of a result from a few years ago where we determined that there are hydrothermal vents at the bottom of that seafloor. But the next question for people is, how did we figure out that there are hydrothermal vents in there without actually going to the bottom of the seafloor after everything we've learned about Europa? So I figure we should probably talk a little bit about that result, because there are, in fact, reasons why we do think that there are hydrothermal vents down there.
There's actually a surprising, to me, amount of information about this, because Enceladus is much smaller than Europa. It's not hanging out next to big moons, but it's got these plumes that are going often enough that you can just fly through them. It's not easy, but Cassini flew through them, and when they did, they had instruments that detected all sorts of goodies that would be consistent with having hydrothermal vents producing things, including molecular hydrogen, which is something that you get produced at Earth's deep sea hydrothermal vents. Found little tiny silica grains that were consistent with the type of thing that you also generate from taking mineral-rich water and slamming it into cold water, as happens at the deep sea hydrothermal vents, and is very similar to those. You've got chemistry that with methane and carbon dioxide and ammonia and the ratios of them and the isotopes that gives some indication that you've got recent water circulation. So you're never sure, or at least I am never sure, when you've got something that you're trying to figure out 1.5 billion kilometers away. But the fact that you see all of these things really would be quite consistent with hydrothermal vents and a rocky, warmer, chemically active floor. So it's kind of weird, kind of wild, kind of new, kind of wow.
Yeah. And why does that moon have hydrothermal vents but not others? Like, there's so much we don't understand. I don't know. I love hydrothermal vent systems because I've spent a lot of internet rabbit hole time looking at videos at the bottom of the Marianas Trench. And especially those little see-through shrimpies without any eyeballs that just live down there. There's so many wacky creatures in those vents.
No, they're very, very bizarre. The white crabs, the tube worms. I mean, it's a whole freaky thing, which is not surprising considering it's a totally an ecosystem based upon chemical energy rather than solar energy, which is the reason people were able to say, look at that we actually could have life on a subsurface ocean like Europa or Enceladus. I mean, you may not get it for all sorts of reasons, but the fact that you didn't require solar energy, since those oceans are so deep, they're not getting any light, it opened up a whole world of worlds.
Right? Those little guys have no idea they're living on a giant rock plummeting through space. That's awesome.
Wow.
But also true of my cat who lives on the surface. So, whatever.
All right. You ready to move on?
Let's do it.
Random Space Fact Rewind!
So with the upcoming, whenever it occurs, launch of Artemis 2 to go fly around the moon and back, people often think, hey, we go to the ISS, International Space Station, all the time. Why is it so hard to go to the moon? I mean, besides getting onto the moon? Well, primarily because it's a lot farther away. It's, if you think of it as like heights, you have to go 1,000 times higher, 1,000 times farther, although you get the orbital mechanics of what you actually do with the elliptical patterns. But it is 1,000 times farther away than where the ISS orbits.
That's a long way to go. I remember my first car, actually, I celebrated when it hit that distance to the moon marker because it was an old car.
Wow, an old car, you got a lot of mileage out of it.
Oh, yeah, drove that thing forever.
Ballpark 250,000 miles, as I recall.
Yeah.
400,000 kilometers-ish.
That was a long way. Man, I'm wishing so much good upon the people doing this mission. This is a huge thing. But can you imagine, after all these years, being one of the people that get to go around there and people flying around the backside of the moon? Oh, it's cool being in the Artemis era.
All right, everybody, go out there, look up in the night sky, and think about the backside of water. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review or a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, you can leave a comment in the Planetary Radio space in our member community app. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members all over this planet. You can join us and help support the search for life on other worlds at planetary.org/join. Mark Hilverda and Ray Paletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. I'm Sarah Al-Ahmed, the host and producer of Planetary Radio. And until next week, Ad Astra.